Hello, welcome back to the Pink Chemist. So today we are here to predict products. All right. So before we get into doing some examples for predicting products, I'm going to write out a few tips to remember when it comes to predicting products. Now, if you haven't already, you should definitely go back to my first video on type of reactions. That way, it'll be easier for you to understand how to predict products by understanding the 5 types of reaction that we will go over today. All right, so let's get started. All right, so some tips for predicting products. All right, so tip number 1, okay, you're going to determine the type of reaction. Now, this is important to know because there are 5 that we're going to go over today. So we have single replacement, which I like to call the reaction that you start off with a couple and a single in the reactant. Okay. And one person gets replaced in the product. All right. Number 2, you have double replacement. Now, if you're one of my students, we use the verbiage of saying that in the reactant, in a double replacement, you have 2 couples. Okay. And what we mean by 2 couples is basically that you have 2 compounds. Okay. Oops. That makes sense. All right. Number 3, we have synthesis. I can't spell. Hold on. Okay. Sorry about that. But I have a synthesis reaction. And the synthesis reaction is what I like to call the couple. Okay. Because in the product, you have a couple coming together or a compound coming together. So in the reactant, you will have either 2 single elements or 2 substances that come together to produce a couple. Okay. 4, we have decomposition. Okay. And this is just a quick overview. Okay. This is what I like to call the breakup. Now, this is not scientific at all, but this is how I help remember the different types of reaction, but the breakup. And then in the breakup is when you have in the reactant, you start out as a couple, but then in the product, that couple breaks up. Okay. And then lastly, we have combustion. And then combustion is the easy one. All right. In a combustion reaction, it produces H2O and carbon dioxide. You must have both in the product. You also can identify a combustion reaction where in the reactant, it produces an oxygen gas. Okay. So those are some things or some quick tips to help you to determine the type of reaction that's at play. Next, tip number 2. It has to make sense. All right. Now, there are some subparts to it having to make sense because once you identify your type of reaction, you then have to follow the law or the rule of that reaction to follow out step number 2. So, for instance, if you have a single or double replacement, okay, the step that you have to follow is that you, for one, have to make sure that the metal is paired with a non-metal. This is very important. If you do not understand this, it will be very difficult for you to predict the product. Okay. Once you understand that your metal is going to be paired with a non-metal, you must keep the metal in place and then you move the non-metal. All right. This is important. Now, another key that I want to go ahead and stamp right here that I share with my students is that your metals are identified by having a positive charge. So if you have a positive charge, that you know that that's your metal. If it has a negative charge, you know that that is your non-metal. Okay. So that's just a little tip that I want to go ahead and make sure you have. All right. Now, the next type of reaction, if you have, is if you have a combustion reaction. Okay. So if you have a combustion reaction, this is the easy one. This is what I like to call the easy one. You don't have to worry about doing too much. All right. So your combustion is easy. You can identify your combustion because it will always have an oxygen gas, which is identified by O2. Okay, it's a diatomic element on reactant side. Okay, then on the product side, you will always produce CO2 and H2O on the product side. This is how you know that you have a combustion reaction. Okay. Next, another tip to follow is that when you have decomposition, this is what I like to call the breakup reaction. Okay. You're going to follow the rule of separating the metal from the non-metal. Now remember, earlier I shared that metals are identified by having a positive charge and non-metals have a negative charge. And if you're my student, we're talking about charges, you know that I'm also talking about the oxidation number. And you can find that at the top of your periodic table, or at least you should have it at the top of your periodic table from when we wrote it in class. For those of you that's not my students, I will have a video that I will upload about how you can put information on your periodic table that will help serve you the way that it does my students. All right. Lastly, we have a synthesis reaction. Now, these steps are very important because once we get into doing examples, it's important that you're able to go back to the steps. All right. So that you can keep track as to what you're doing. Now, in this video, when it comes to a synthesis reaction, because you can form so many products, we're just going to stick to one synthesis reaction. All right. So we're not going to go into depths of all the different products that can be produced from a synthesis reaction. We're only just going to do one type, and you will see that once we get to that part of the video. Okay. All right. So hopefully you have your tips. All right. So let's get into our examples. Okay. Oh, actually, it's one more step. One more tip. Sorry about that. So the last tip is you must remember your IUPAC rules, okay? Remember your IUPAC rules. Well, what are IUPAC rules? I'm glad you asked, even though you did it. But I'm sure there's some of you that probably have questions. So first, remember that for your ionic bonds, okay? Ionic bonds, you must pair a metal with a non-metal. Okay. Your metal always comes first. If you put your non-metal first, you do not have an ionic bond. Okay. This is important. Once you do the process of pairing your metal with the non-metal, you also must do the swap and drop. Okay. You must swap and drop. And in order to swap and drop, you're going to need oxidation numbers. All right, so if you're my student, you know that you have to swap and drop with an ionic bond. If you have a covalent bond, all right, you must have two nonmetals paired together. But for the sake of this video, I'm not going to go too deep with covalent bonds because the examples that we're going to use are all going to include ionic bonds. All right. And then lastly, don't forget your diatomic elements. All right. Your 7 diatomic elements is H2, N2, O2, F2, CO2, Br2, and I2. Okay. Your 7 diatomic elements must always be paired with the subscript 2 because in nature they are never found alone. Okay. This is very important. Now, I also want to note that when these elements are by themselves, they are in a gaseous state. They're gases. Okay. All right. So let's get into our examples. All right. So here we have HGO starting in our reactant. Okay. So we have HGO started in our reactant. Now our first step is to identify our type of reaction. Okay. So we know that Hg, okay, is a metal, and we know that O is a nonmetal. Okay. O is a nonmetal. So with that being the case, and if you don't know, you have to definitely consult your periodic table. All right. So the fact that I have a couple starting in my reactant side, I know that I'm going to have a decomposition. I got a decomposition reaction, and that D is just me identifying that this is a decomposition reaction. And now in my tips earlier, I learned that when I have a decomposition reaction, that means that I have to separate my metal from my non-metal. So I'm going to separate Hg plus O. And because I have to follow the rule of my diatomic elements, out of the two, I know that oxygen falls as a diatomic element. So I am going to pair it with the subscript of 2. And I'm finished. All right. That was pretty easy. All right, next. Our next example. We have Al plus Pb NO3, 2. Now, this is what I mean by when it comes to what we call a single replacement, right? So this is going to be a single replacement reaction, okay? And I know this because here I have Al, which is aluminum. It is a single element. So I have a single element here, and then I have PbNO3, all right? So with me having PbNO3, I know that this is a couple, okay? Couple meaning 2. I have 2 separate elements that come together to create a compound. So with that being the case, when I have a single and a couple, or a single element in a compound, I know that I'm likely going to have a single replacement. All right. So if I have a single replacement, that means one of these elements are being swapped. Okay. Now in our tips earlier, we learned that we have to make sure that our metal is paired with the non-metal. We also learned that we have to keep the metal in place. Okay. So for this one, okay, I'm going to go ahead and keep the metal in place. Al, I know that it is a metal. So I'm going to go ahead and keep it in place. So I got Al. And I'm going to keep that in place because it's not supposed to move. Now, when we're talking about it not moving, we don't mean that it doesn't move from the reactant side. Because remember, the reactant is what our reaction starts with. Our product is what's actually produced. Okay. So I'm going to just go ahead and keep Al, my metal, in place. Okay. And then when I go over, I know that Pb is a metal as well. In fact, it is a transitional metal. So with that being the case, I'm going to go ahead and keep Pb in place as well. Okay. Now, when I get to NO3, I know that NO3 is a polyatomic ion, which is also identified as a nonmetal. So my nonmetal is the only thing that is being moved. So since my nonmetal was already paired with PB, I'm going to go ahead and move it to the other single metal, okay, which is Al in this case. Now, a common mistake that is made is that oftentimes people see this 2 right here, this subscript of 2, partner with NO3 as a subscript, and they would like to move that subscript with NO3. But that would be inaccurate, because if I did a reverse swap and drop, I learned that that 2 comes from right here. It comes from the oxidation number of PB. And now that NO3 is no longer paired with PB, I don't need that 2. But in order to finish off my actual product, I have to now follow the rules of when I have a metal and a non-metal paired together, which is an ionic bond. I have to finish the rules of what it means to have an ionic bond. So now I have to swap and drop. So Al, okay, if I look at my periodic table, I know that Al has an oxidation number of positive 3. All right. NO3 has an oxidation number of negative 1. I now have to finish the process of swapping and dropping. When I mean swapping and drop, I mean that I'm taking my oxidation number and I'm swapping it down to the opposite element as a subscript. So do you see where my arrows is pointing? That arrow is letting me know where that number needs to come as a subscript. Now, when we're writing a subscript, we never bring the charge. We're just going to bring the number. So for my finished product, I'm actually going to have Al. We also do not write 1s as a subscript, because it's already understood that if there is no 1 there, that it's already 1. Okay. I got NO3. And I'm going to bring this subscript 3 outside of the parentheses. Okay. We don't want to bring anything inside the parentheses. And that is my product. Okay. That is my product for my single replacement. All right. Let's go to the next step. Okay. For the next type of reaction. Example. All right. So our next example, we have AgNO3 plus K2SO4. All right, so this one, I'm going to go about it just a little bit differently. So I'm going to go about this, and honestly, there's ways that you can make this work for you, but for the sake of really breaking down, because I do understand how confusing this can get, and I've seen that this method has actually worked for some of my scholars, so I'm going to go ahead and share this with you all. All right, so when it comes to the reactant side, all right, we're already in the process to where we have swapped and dropped. Now, what I'm going to do is go ahead and identify my oxidation number for each element. That way, I can just start plugging in once I get to the product side. All right. This will also help me with identifying whether I have a metal or a non-metal. Okay. So here for AgNO3, I see that I have a subscript of 1 for both elements. So that means 1 or 2 things. That means that either this compound has been simplified, or both of these elements, Ag and NO3, has an oxidation number of -1 and +1. The only way for me to find out, because Ag is a transitional metal and it can have multiple oxidation numbers, the only way for me to find out is to first identify my oxidation number for my nonmetal. And what I know is that my oxidation number for my nonmetal, which is NO3, is -1. And being that my oxidation number for NO3 is -1, I know that my oxidation number for Ag has to be +1. That will only make sense for me once I do the reverse swap and drop to see why my subscripts here, which you don't see a subscript. If you don't see a subscript, it is automatically out of assume that your subscript is 1. All right, so that matches up with what was already there. So good. Now, when it goes to K, potassium, I know that potassium has an oxidation number of positive 1. Okay. And then for SO4, I know that I have an oxidation number of negative 2. I know this to be true because when I swap and drop, you see how that 2 is there? That is where that 2 comes from, that oxidation number. You see how there is no oxidation number here, which lets me know that it's 1. That is where that 1 comes from, that oxidation number after we swapped and dropped. So now that we got that out of the way, we can go ahead and go about predicting our products. So I know that, we didn't identify the type of reaction. All right, so for the type of reaction, okay, we have AgNO3. I know that this is a couple, okay, and then we have K2SO4. I know that this is another couple. When I have 2 couples in my reactant, I know that I am going to have a double replacement. So 2 of the elements are being replaced. Now, what I do know is that the tips above shared with me that I'm going to keep my metal in place. When I look at Ag, I know that Ag is a metal. I can also tell that it's a metal because it has a positive charge. And so when I have a positive charge, I know that my positive charge elements are metals. They're acting as a metal, okay? So I got Ag positive 1. All right, so I'm going to go ahead and keep that in place. Now, when it comes to NO3, I know that it has a negative charge, which means that it's a non-metal. And I know that for double replacements, I have to move my non-metals. But right now, I do not have a metal to pair it with, so I'm going to just keep it right there just until I get my next metal, okay? So then I'm going to come over to K, all right? K is my metal. So I'm going to go ahead and keep K in place, okay? So now that I have my metals in place, I'm going to go back and I'm going to swap out my non-metals, okay? I'm going to swap these non-metals out, all right? So I am going to swap NO3 out from Ag and bring it to K. All right? And then I am going to swap SO4 with Ag. All right. So do you see how I was able to add my oxidation numbers once I got to the product side because I had already written them on the reactant side? Now, you're not required to do this, but just for those of us that kind of need like a step-by-step process, this definitely is a method that will help you. Okay. So next, we are not finished because now we have to go through the process of swapping and dropping. If you leave your oxidation numbers at the top in your products, this will be incorrect. You must finish your products by doing the process of swapping and dropping and bringing your oxidation numbers down as subscripts. Okay? And so what we know is that from here, we're going to have Ag2. You see how that 2 literally came from that oxidation number, Ag2, SO4, and because we do not write ones, we're going to leave it there. And then we have KNO3. And that is our product for our double replacement. All right. I really hope that this is helping you, okay? Next, we're going to go to our next type of reaction. So we have CH3OH plus O2. I'm seeing an O2 here. All right. So we learned that in the reactant side, when we see an oxygen gas, which is O2, that we likely have a what type of reaction? A combustion. Okay. A combustion reaction. Okay. So since we have a combustion reaction, and also for combustion reaction, you will see that you will have a hydrocarbon, CH. And when you see CH in your reactant side too, you also have the presence of a hydrocarbon. All right. So being that I have a oxygen gas and hydrocarbon in my reactant, I know that on my product side, what's going to be produced is CO2 and H2O in order for it to be considered a combustion reaction. And we're just going to keep it that light and simple. You don't have to do anything else as it relates to combustion reaction for these steps alone. And you're done. And then for our very last type of reaction, okay? You have two elements, okay? You have two elements that are separated from one another, okay? So you got H2 plus O2. That means that in the product side, they're likely going to come together to become a couple or one compound, okay? So with that being the case, I know that this is actually my synthesis, okay? This is a synthesis reaction, all right? Now, when they come together, they're going to come together to produce H2O. Now, this might confuse some of y'all because it's like, wait a minute. How do they come together as H2O, and what happens to their subscript? Like, what happens to the subscript of 2 with the O2 if the 2 followed the H? Well, let me show you something really quickly. And this will be very key to go ahead and write this down. Now, when you're doing a ionic bond, your ionic bond must have a metal and a non-metal. All right. So in this case, we're going to use hydrogen and we're going to give it a +1 charge. Now, hydrogens, it can act as a non-metal as well. But in the case of H2O, we're going to go ahead and have it act as a metal, which it will have a +1 oxidation number. And then for O, we know that the oxidation number is -2. Okay. Now, with that being the case, we're going to go ahead and swap and drop. And when we swap and drop, we have H2O produced. So this subscript of 2 actually comes from the oxidation number -2 from oxygen. It doesn't come from the subscript of H being by itself. Okay? Remember, H2 is a diatomic element, as well as O2 being a diatomic element. And with that being the case, you have to pair it with the subscript 2. All right. So because we follow our IUPAC rule over here, this is how we got hydrogen. I want you to keep that in mind because that is very important, because sometimes you might get examples and you may think that all of your elements are non-metals. And in fact, your hydrogen for H2O is acting as a metal. Okay. So go with it, whatever your professor or your teacher teaches you. But for my students, this is definitely important for you to remember based off of the steps that we're going through as we navigate through each lesson. Okay. Well, that is the end of our video. I hope these examples help. And until the next video, have a good day.